So we're trying to look at ways to describe these electric fields that we're calculating. And so here we have two charges, a positive charge and a negative charge. And you can see that this is a simulation. This is a screenshot of a simulation that's showing you the direction of the electric field. And if we take a point, say right here, then we're some distance away from this positive charge right here, and we're a different distance obviously away from this negative charge, and so these vectors add up. This might be in this direction, would be the direction of the electric field. This would be like that, but it's not as long. So let me undo that. It would be shorter, and altogether we're left with a net field that's sort of in that direction. That's the overall net field. And so what this does, instead of doing lengths to show the size of the field, it uses colors. So as you can see, the bluer color out here, the more faint blue purpley color, means a weak field, and a strong field is red or green or even black or brown, as you can see. So this is just a color representation of the field. Now, it's hard to draw this in your notes because it's hard. You have to switch colors of your pen. It's not like you have a nice color palette. And so what we do is we often describe this by something called electric field lines. So field lines are basically, we just connect these arrows. So I might connect the arrows and say like this. I might connect these arrows like that. And what the field lines do is show you that the electric field is tangent to the field lines at any point. So if I look at this right here, that's the direction of the electric field. Here, that's the direction of the electric field. And so for this configuration then, this is our electric field line. And they leave positive charges because that's the direction the electric field points, and they go toward negative charges because if I have a positive charge right here, it really wants, that's the direction of the force that it feels. And similarly here I've got charges that go like this and ones that go in here and along here. And so this is my charge, my electric field line distribution. And so you can see I'm sort of setting this up as we go here. But notice in the middle we have the bending because that's the contribution of the electric field from the two particles. So these are, this is a dipole. This is a dipole. This is the charge configuration of a dipole where I've got a positive charge here and a negative charge here. So that's a dipole. Now we can have two charges, each of +1 or -1 in whatever units we're talking about. This is a configuration where, or +3 and -3, this is a configuration where they're both positive charges. So they're equal charges, but they're positive. And so if I'm going to draw the field lines for this, notice that this kind of curves up this way because the because if we put a test charge here, a positive charge, it would be repelled from this, but also would be repelled from this, so that from this charge, the lower charge over here. And so similarly, if I put a little positive charge here, it would feel force, and then it kind of goes this direction. Okay, so these are our field lines. This is not the direction that a charge would move, right? Because once something starts moving, it doesn't have to follow the field lines, okay? And I'll give you an example of that in just a minute. But here's where we go. These are electric field lines like this, and so forth. Okay, so those are our electric field lines for this. And then finally, this is a more complicated system. We don't even know what these charges are. We can get the idea that 1 and 4 are stronger charges than 2 and 3. But if we look, then we can draw our field line diagrams. We can sort of, again, we're just connecting these little arrows. This is our vector field orientation. Notice that 4 must be negative. 2 is kind of a positive charge, and 3 is negative, obviously because the arrow's going towards it. We'll let's see, that's coming from back over here, sort of, and 1 is a positive, it's a positive charge, and so forth. So something like that. And in fact, in this particular illustration, this is a fizzlet, you can see that this calculates to this as your field line representation, which you can see here. So it's convenient to sort of draw in the field line representations. So here we have a situation where we have a test charge, and what I mean by test charge is one that doesn't impact the field lines, but I can still feel the force from the charges. And so you can see this force arrow as I move it around. Notice as I'm close or far away from one of these charges, you can see the force, and the force is pretty big, and the force is pretty big over here. Now if I let it go, what we're going to see is I'll put it on this field line right here where it sort of looks like it's lined up, and what you can see is, so you can see here it is, it's on, it's set up, ready to go, and then I hit play, and you can see the green path that it takes, and then it goes off the screen. Now notice that as it started along the field line, but because it had momentum in that direction, it continued going across the screen and didn't just follow the field line, okay? So if we look at that, that's what we see. So this test charge followed this for a little while, but because it had momentum in this downward direction like this, then even though this force is pulling it down, and this one is, notice if I'm right here, this is repelling it, so that the force is sort of, the electric field is down over this direction a little bit more. Well, that's the field line here. It's going to be like that. This is still going to keep its momentum. It still wants to move away from these two, but it's not going to stick to a field line because it's got its momentum. You can think of this as, in the equivalent case, when we're standing on the Earth. So here's the Earth. The field that we're in, the gravitational field, is straight down. So that's the gravitational field. At least close to the Earth, right? If we get far away from the Earth, it's sort of radially in. But the gravitational field is down, but we can throw an object, right, in this direction. We can send it with an initial velocity in this direction, and it follows a trajectory like this. It doesn't just immediately go straight down. Certainly, if we just let it go, it goes straight down. But in general, if we get it started with some speed, it's going to follow the trajectory. Well, you can think of this particle, right? It starts initially at rest, so it follows the field lines, but then it's going, and because the field lines aren't just straight, it starts to not follow the field lines, just like this ball in the path right here. So the field lines tell you, again, the field lines, if we scroll all the way back here, they tell you that the electric field is tangent at that point. So right up here, that would be the direction of the electric field. That would be the direction of a force on a positive charge. But if the positive charge were already moving, say, in this direction, then it's not going to suddenly just change, do a right turn like that. It's going to do more of a trajectory like that, okay, and then curve.